All right, so the next talk is Ben Safdi, and the title of his talk is The Milky Way's Gamma Ray Mystery, Dark Matter, or Astrophysical Point Sources. Paul Schechter is one of the great wags of this department, and one of the things he's told me is any paper with the title in the form of the question, the answer is always no. However, this is a violation of that. So I'll leave it to Ben to explain.
I don't think this is a yes or no question. So today I want to tell you an interesting story about a mysterious glow of gamma rays that's been seen emerging from the center of the Milky Way and possible connections to dark matter physics. But I want to begin the talk with a bit of a historical introduction to dark matter. So one fact about dark matter, which I think isn't often appreciated, is we've actually known about the existence of dark matter for quite a long time. So dark matter was first discovered by the physicist Fritz Zwicky, who was born in Bulgaria. He grew up in Switzerland and spent most of his academic career in the United States at Caltech. And if you go to his birthplace in Bulgaria, you'll see this plaque, and on this plaque it reads, "In this home was born Fritz Zwicky, the astronomer who discovered neutron stars and the dark matter in the universe." So we've already heard some about neutron stars today, and in fact, both neutron stars and dark matter will feature prominently during my talk. So how did Zwicky first discover dark matter? So he discovered dark matter by staring deep into the Coma cluster of galaxies. Here's a modern image of the Coma cluster taken by Hubble, and he went through the following exercise that I want to lead you through. But first, let's look at this cluster. This cluster consists of tens of thousands of galaxies, and each one of these galaxies is like our own Milky Way. It has billions and billions of stars. So this is some huge object in the sky. And Zwicky went through the following exercise. Let's imagine first that none of these galaxies are moving. They're all stationary with respect to each other. None of them are moving. So what would happen? Remember, gravity is always attractive. So this system would simply collapse onto itself. And that clearly didn't happen since this system is still here today. So now let's imagine the opposite regime, where the galaxies are each moving very quickly with respect to each other. Then what would happen? The gravitational potential will not be able to hold in these galaxies, and this system would simply evaporate. So because the system is still here today, there must be some balance between the kinetic energy of these galaxies and the gravitational potential holding them together. So by measuring the average kinetic motion of these galaxies, Zwicky was able to infer the total amount of gravity, or the total matter inside of the system. And he came to the very surprising conclusion that most of the matter in the system is non-luminous dark matter. So this is my attempt of translating an original sentence from his paper, which was in German. And at least Google tells me this reads, if this would be confirmed, we would get the surprising result that dark matter is present in much greater amount than luminous matter. And in fact, today we know this is correct from a variety of measurements over the past 80 years. And today we know that around 90% of the matter in our universe is non-luminous dark matter. So moreover, we know that dark matter doesn't just play some passive role in the formation of our universe. So like Jesse, I am not a biologist, but if you ask me, dark matter is key to life. So what do I mean by this? I mean that without dark matter, our universe would look unrecognizably different to us today. So dark matter is key to forming the structure that we know of that's necessary to have structure like us, like humans. So here I'm showing you a video of an in-body simulation looking at the evolution of our universe. Here's a slice at some very early time. This is the dark matter you're seeing here. So we have a roughly isotropic, homogeneous dark matter distribution, except for small perturbations. Now, as they evolve in time, these perturbations collapse, forming structures like clusters of galaxies, galaxies which form things like solar systems and things like humans. So we know that dark matter plays a very important role in our universe. We know a lot about dark matter. But at the same time, dark matter is quite mysterious to us. So we have no evidence for non-gravitational interactions of dark matter. All of the evidence we have for the existence of dark matter is gravitational. And we also have no evidence for any particular dark matter mass. And these are the questions which I'm going to be addressing today in my talk. These are the questions that I personally am very interested in. And these are the types of questions that I think as a community we're trying to answer right now. However, this marks a clear transition in my talk. Everything that I've told you up until now has been very well established, is fact. But when I start talking about these non-gravitational interactions, I necessarily have to start speculating, because we haven't observed these yet. So I have to talk about some particular model for how dark matter might interact with the rest of nature in a non-gravitational way, and then how can I search for dark matter within the framework of this model. So just keep that in mind for the rest of my talk. So one very nice class of models, which I'll focus on today, are so-called thermal dark matter models. And one nice aspect of these models is they're detectable through a framework called indirect detection. And I want to sketch how this framework goes here. So in this class of models, we imagine that in the early universe, dark matter is in thermal equilibrium with the rest of ordinary matter. And as the universe expands and cools down, and I'll explain this in more detail, at some temperature, dark matter falls out of equilibrium. And then there's dark matter annihilation into ordinary matter that sets the relic abundance of dark matter that's left over. So dark matter annihilation is the process by which a dark matter particle and its antiparticle collide, annihilate, forming ordinary matter. So the leftover dark matter that didn't annihilate gives a structure that we see, for example, in the cosmic microwave background, which evolves, as I showed you in the movie, into clusters of galaxies and galaxies that we see today. Now, if we concentrate on one of these galaxies today, this could be our own Milky Way. This galaxy is surrounded by a halo of dark matter. And since in these models, dark matter annihilation occurred in the early universe, it can still occur today, giving us cosmic rays which can stream into our detectors. And today I'll be concentrating on Fermi, the Fermi telescope, which sees gamma rays. So after Fermi launched as a space-based telescope back in 2008, something very exciting happened in this field. An excess of gamma rays was observed around the center of the Milky Way, consistent with arising from dark matter annihilation. So here I'm showing you a full sky view of the sky as seen by Fermi. You can see the plane of the Milky Way, our own galaxy, cutting clearly across the image. The galactic center is directly in the middle. And when you subtract off the predicted contributions from standard astrophysical processes, you find this nice spherical residual right on top of the center of the Milky Way. And this is exactly what we would expect if what we're seeing here is dark matter annihilation. But what I think is the most interesting part of this excess, if we interpret it in the context of dark matter annihilation, we find a very special rate for dark matter annihilation that we need to explain the normalization of the data. So I'm going to refer to this rate by a cross-section. And you can think of this cross-section as a probability of if a dark matter particle and its antiparticle collide, what's the probability they actually annihilate. So I'm going to describe this by a cross-section, and we need a special value around 3 times 10 to the minus 26 centimeters cubed per second. And this value is so special because it's exactly what we expected to find. And it's what we expected to find because this value explains the abundance of dark matter that we see today in our universe. And I want to explain this in a little bit more detail. So we have this picture. Right after the Big Bang, up here, the universe is a hot gas. And as time evolves, the universe expands and this gas cools down. So what does it mean for a gas to be hot? That means that the energy of the particles in this gas is very high. So in this case, we can have 2 types of processes, dark matter annihilation, which I already told you, and also dark matter production. So here, 2 ordinary particles collide, and they form dark matter. And this process can happen, we're imagining the dark matter is much heavier than the ordinary matter, but this process can happen because the ordinary matter has a lot of energy. So when they collide, they have enough energy to produce this heavier dark matter. But when we're at lower temperatures, well below the dark matter mass times c squared, we can't have dark matter production anymore because when the ordinary light particles collide, they simply don't have enough energy to produce this much heavier, much more energetic dark matter. But we can still have dark matter annihilation, and this process will occur depleting the abundance of dark matter. So the larger this rate, the larger the cross-section, the less dark matter will be left over with at the end of the day. So then it shouldn't be too surprising that there's only one value for this rate for which this picture actually works, for which we actually get the correct abundance of dark matter. And it involves that same exact cross-section that I showed you explains the overall normalization of the Fermi data. So this has led to hundreds and hundreds of papers trying to interpret this excess in the context of dark matter annihilation because it looks like we're finding exactly what we expected. So are we beginning to solve Zwicky's mystery? Are we beginning to understand the non-gravitational interactions in the dark sector? So this would be very exciting. This would be a revolutionary discovery. This would completely change our field. So I think it's worth being very cautious, especially because the center of the Milky Way is a very complex environment, the variety of backgrounds which could be contributing. And right now I want to try to argue that another very relevant source of background is neutron stars, which is Zwicky's other big discovery from the early 1930s. So more specifically, I'm going to be looking at millisecond pulsars, which are a subclass of neutron stars. So we've already heard about neutron stars. They're compact stellar instates consisting mostly of nuclear matter. They tend to be rapidly rotating, and they emit emission in these collimated beams. When the Earth sits in the path of one of these beams, we call the neutron star a pulsar. Millisecond pulsars are rapidly rotating pulsars, which tend to form in binary systems, we have a massive companion star which accretes onto the neutron star, spinning it up, giving it this very quick period, and we call it a millisecond pulsar. So it's known that millisecond pulsars emit gamma rays, and it's known that the energy spectrum emitted in gamma rays in millisecond pulsars looks very similar to the energy spectrum we observed for this galactic center, this gamma ray excess that Fermi sees. And we also have reasons to suspect that there should be many neutron stars around, many millisecond pulsars around the center of the Milky Way. So in my work over the past few years, I've developed a new method that I want to explain to you today called the non-Poissonian template fit that I can apply to the data to try to differentiate between these two hypotheses. On the one hand, we have the hypothesis that we're seeing emission from dark matter annihilation in the Fermi data. On the other hand, we have the hypothesis that we're seeing emission from a population of millisecond pulsars. So I don't have time to describe this method in detail, but I want to try to give you some of the basic intuition behind this method. And then I'll show you that when I apply the method to data, I find strong evidence that in fact what we're seeing is a population of astrophysical point sources consistent with millisecond pulsars and not, unfortunately, dark matter annihilation. So the basic intuition can be summed up by these images. So here I've generated fake data under two assumptions. On the left-hand side, I'm assuming what we're seeing is dark matter annihilation. And on the right-hand side, I'm assuming we're seeing emission from a population of point sources. And here I'm showing you the excess only without any other backgrounds to make this comparison easy by eye. So in this case, you don't need any sophisticated algorithm to differentiate between these two hypotheses. You can do so by eye. But I want to try to gain some intuition from these images so I can describe an algorithm that I put on a computer to differentiate between these hypotheses when it's not so easy to do so by eye. So with that in mind, let's concentrate on some small regions of these images and try to be quantitative about the differences. So notice I've pixelized the sky. In the dark matter case, you can see that all pixels see roughly the same number of photon counts. But in the point source case, this is no longer the case anymore, because I have lucky pixels which happen to sit directly on top of point sources, which see a large number of photon counts. And because the total number of photon counts is roughly the same between these images, I also have more unlucky pixels which see very few photon counts. So the distribution of photon counts clearly looks different between these two sets of images. So I can make this slightly more precise by actually histogramming the number of pixels which see a given photon count. So in the dark matter case, we end up with the following distribution. And this distribution is known as the Poisson distribution. And I thought I would give an example of the Poisson distribution that's maybe more everyday. So I went through the following exercise and determined how many letters I receive each day. And it turns out it's about 2. I receive 2 letters each day. These are physical letters in the mail, delivered by the mailman. Is that surprising, or? So what does that mean? Does that mean every day I receive 2 letters? No. Some days I receive less. For example, some days I'll receive 0 letters. Other days I'll receive more. For example, some days I'll receive 5 letters. And if I were to histogram the number of letters I receive, it would follow the Poisson distribution, this distribution. In fact, the first application of the Poisson distribution, you might be interested to know, was to analyze the frequency of people getting kicked by horses in the Prussian army in the late 1800s. Now we're using it to try to find dark matter. So the key point is when we have point sources, we end up with non-Poissonian photon count statistics. We end up with a much broader photon count probability distribution because we can have these lucky pixels which see a high number of photon counts. That's what I'm showing in purple. And we also have more unlucky pixels which see very few photon counts. So my analysis utilizes the difference in photon count statistics to try to differentiate between these hypotheses. So when I look at the Fermi data, I find that the statistics near the center of the Milky Way is consistent with having a large population of individually dim point sources and inconsistent with arising from dark matter annihilation. So I don't have time to describe in detail how the analysis actually works, but I want to show you one image that I think sums the picture up pretty well. Here you're seeing a zoomed-in picture of the galactic center. The galactic center is directly in the middle of this image. Red crosses here show you the locations of known gamma ray emitting point sources. So some of these are millisecond pulsars. Some of these are supernova remnants. Others are other astrophysical objects. And in black, I'm showing you places where I find that the photon count statistics are very non-Poissonian. So I think that there should be a point source at the locations of the black circles from the information I have in Fermi. The darker the black circle, the higher my belief is that there's actually a point source, astrophysical point source at that location. If you look around the center of the Milky Way, you can see there's a collection of individually dim point sources. So there's a large ensemble of individually dim and low significance point sources. But when I look at the statistics of that ensemble of low significance sources, I find a high significance statement that I can make, which is it looks like there's a population of individually dim point sources there and not, for example, dark matter annihilation. So Rolling Stone was mentioned earlier, but well, we also have the Daily Mail. So I want to sum up our work, but I think I couldn't do better than the Daily Mail, who described our work by saying, the mystery at the center of the galaxy deepens. Researchers say strange energy is not dark matter. So I actually think their bullet points here do a pretty good job, so I just want to read two of them to you. One, in gamma rays from dark matter, light would appear smoothly across pixels. That's what I showed you in those simulations. Two, image reveals clumpy pixels of light indicating other astrophysical event, that is, indicating astrophysical point sources, potentially millisecond pulsars. So at this point, I think the most important question to ask is, what are these point sources? Are they millisecond pulsars, or are they something else? And to do this, I really think we need to go to some other wavelength. Radio is a very promising wavelength to go to. So recently, I've submitted a variety of proposals to the Green Bank Telescope, and I have more in progress, to try to get radio time to do follow-up surveys at these locations on the sky where we believe there should be millisecond pulsars. So some simulation results that I've done in conjunction with my collaborators suggest that with around 100 hours of time, which is what we're asking for, we could find around half a dozen new millisecond pulsars in the bulge of the Milky Way. And these would actually be the farthest away millisecond pulsars ever seen if we detect them. So finding these millisecond pulsars would have pretty profound implications, both for the galactic center excess. I think this would be very clear evidence that we're seeing emission from point sources from millisecond pulsars and not dark matter annihilation. But also, finding millisecond pulsars is just useful generally. This could indicate some new chapter in the formation history of the Milky Way. And these could be useful for gravitational wave detection using pulsar timing arrays. So hopefully we'll get awarded this time, and I'll have some interesting statements to make in a year or two. So the quest to understand dark matter continues. It doesn't look like we found it yet. But today I've only described one avenue to look for dark matter, indirect detection, and one class of dark matter models. But there are many more ways of searching for dark matter, and there are many more dark matter models. So we can try to directly produce dark matter inside of colliders, and people here in the CMS group think about this. We can try to detect dark matter scattering on our detectors underground. People here also think about this. We can try to search for completely different types of dark matter models, such as axion dark matter models, which require completely different technology. And we're also starting to think about some of this here at MIT. But this is the subject of another talk. So my opinion is we need to take a very broad approach to the search for dark matter. And to illustrate that this is my opinion, I'm showing you here some of my recent papers on these various subjects to show you that I think the approach that we need to take is to be very broad in our search for dark matter. And hopefully in the relatively near future, we will begin to unveil this mysterious dark sector. But the moral of the story that I'm telling you today, I really think is we should always be open for the unexpected. When Zwicky stared into the Coma cluster in the early 1930s, I don't think he had any idea, definitely didn't have any idea that he would find this mysterious dark matter. And this really revolutionized our field over the previous 80 years, and for example, led to Fermi looking deep into the Milky Way in 2008. And instead of finding dark matter, it looks like we might have found something else unexpected, perhaps an unexpected population of millisecond pulsars, which would also be very interesting. So who knows what future searches for dark matter will unveil. So one nice aspect of this project for me personally is it's brought me into contact with a large slice of the MIT physics department. So including professors who either work directly with me on this analysis or on related analyses. Wei, postdoc who's here, graduate students, and even an undergraduate who worked on some of this work with me. And of course, I want to thank Jane and Neil for making both my work possible along with all of the other nice projects that we're hearing about today. Thank you.
Questions from the front row, and then Salvo.
Why is it obvious that dark matter particles annihilate with anti-dark matter particles?
It's not. It's not obvious. So it's not obvious that there even are anti-dark matter particles. So this was the caution, which I was mentioning earlier at the very beginning of my talk. We don't know anything about the non-gravitational interactions of the dark sector. All we know is how dark matter All we know is how dark matter interacts gravitationally. And so when we start talking about searching for these non-gravitational interactions, we have to think of a particular model for how dark matter might interact non-gravitationally with ordinary matter and with itself. And in some of these models, dark matter can annihilate. Not in all dark matter models. So this method of searching for dark matter will work in one class of models. It won't work in another class of models, which is why at the very end I said we need to take many different approaches to our search for dark matter because we simply don't know how it interacts. And so we try to look on all possible channels.
Salvo.
When you said that you favor the pulsar and the millisecond pulsar hypothesis, can you quantify the bias factor or noise ratio?
Quantify the what?
The bias factor or a noise ratio. So how much more sure you are that is
Yeah, so I can quantify this statistically, and then including systematics, it becomes harder. So if you just want a number to think about, I would say that the actual analysis, what does it tell me? It tells me that the pulsar interpretation, or more specifically the point source interpretation, is favored by a Bayes factor on the order of 10 to the 10. So if you want to think of a number of sigma, I think you would take the log of that, multiply it by 2. That gives you a test statistic. Take the square root of that. That gives you sigma if you want to approximately go from Bayesian to frequentist statistics. So we're talking about like 6 sigma, 7 sigma detection over dark matter. However, that does not include systematics. And systematics are important, but they're also very hard. It's very hard to properly account for systematics in such an analysis because astrophysics is complicated. But even when we account for systematics, we find a very robust preference for point sources. Yeah.
Alan.
I'm not sure if I understand this lucky pixel, unlucky pixel way of looking at things. Let me just ask a couple questions. If I have a vial of radium and measure the number of counts I get per second, that's Poisson statistics, right?
Yeah.
Now, if I then add to this vial another vial that has 10 times as much radium and measure the number of counts I get per second, it's a higher rate, but still Poisson.
Still Poisson statistics.
Right?
Yep.
So how does this lucky pixel, unlucky pixel business work?
Sure. So the key difference is, and I was kind of glossing over this, it's non-Poissonian statistics as a function of my model parameters. So if I have point sources and I know where they are, then it's true that I have some smooth background with Poissonian statistics. If I put a point source there, the statistics are still going to be Poissonian. But now I'm assuming that I know where my point source is. When I have a population of dim point sources and I don't know where they are, then as a function of my model parameters, I first have to ask the question, in my lab, what's the probability I have radium? So I don't even know if it's there. And then given that I have radium, what's the probability it gives me this number of counts? So I have to ask multiple questions. So I end up in some sense with a double Poissonian distribution. Because first, in a given pixel, I have to ask, what's the probability I have a point source there in the first place? And then given that point source, I have to ask, what's the probability it produces so many photons? So it's because that we're ignorant in some sense about where these point sources actually are. As soon as we know where one is, we can fix its location. Our statistics there become Poissonian. Does that make sense?
I'll think about it.
Okay.
So in terms of current models or simulations of galaxy evolution, do these millisecond pulsars fit in nicely, or is it just way too early? Do we just not know enough about galaxy evolution to know whether that's plausible or not?
They fit in nicely into models which were written down after this excess was measured. I don't know if anyone would have predicted this ahead of time. But there are models which I think are very reasonable explaining this population of millisecond pulsars. One of the models that I like best looks at merging globular clusters. So globular clusters are very dense stellar environments. And because they're so dense, they tend to have many binaries. They tend to have a lot of low X-ray. They tend to have a lot of millisecond pulsars, also low mass X-ray binaries. And when these globular clusters merge with the Milky Way, they can be tidally disrupted, and their contents can be essentially spilled out around the Milky Way. And so people have taken models for globular clusters in the Milky Way and evolved these models, and then taken known information about the gamma ray luminosity coming from globular clusters, which is mostly due to millisecond pulsars, to infer what the flux should look like in gamma rays. And you get something very similar to what's seen in this excess. But this was a story that was written down after our work in particular. But yeah.
But you suspect they're millisecond pulsars because that's characteristic, the gamma rays are characteristic of millisecond pulsars.
Yeah, so there are a few reasons.
So you have to do a broadband radio search.
Yes, yeah. So from the information we have in gamma rays, we can't say conclusively that they're millisecond pulsars. We can't see pulsation. Most of these pulsars would only contribute 1, 2, 3 photons over their entire course of the Fermi. However, the energy spectrum that we see in the data looks just like the energy spectrum that we see when we point the telescope at a millisecond pulsar. So this is, you can take as a very strong hint. Also, from this analysis, I get back a luminosity function, a best fit luminosity function for this population of point sources, which is suspiciously close to what you would expect for millisecond pulsars. So there is a lot of indirect evidence hinting towards millisecond pulsars.
One more question. Yes?
Is there any hint about the spatial distribution of dark matter and with this point-like business versus possibly dark matter? Does it mean that you suppose that it's homogeneous and not point-like?
So maybe I can show you this. So here you can see this residual. You can see it's very bright at the center, and then it falls off. So the dark matter distribution is not like the baryons. So the baryons are in a plane, and it's because they're pretty strongly interacting. They have dissipation. Dark matter is expected to be this diffuse halo, but it's still, the density falls off as you move away from the galactic center. And then dark matter annihilation, what we expect to see is essentially the dark matter density squared, because two particles have to find each other. So you have to ask, what's probably there's dark matter twice? And that's essentially what we see in the data. However, in the region where we can actually look, the dark matter density is essentially just a power law. It falls off like 1 over r to the 1 point something. And so the signal that we see in the data, the signal falls off like 1 over r squared as you move away from the center of the Milky Way. And there are many other, there are other phenomena that you would expect would fall off like 1 over r squared in these regions of the Milky Way. So by the spatial information alone, yes, it's a strong hint, maybe that it has something to do with dark matter, but there are other populations, such as millisecond pulsars, that we'd also expect to have that same spatial fall off.
Let's thank Ben again.